Hi everyone. So today we'll understand how to use internet ADC of MSP430, and we'll write program at the end to demonstrate how to convert analog input to digital. So every embedded system we might have interfaced sensors and transducers. Each sensor and transducer will sense the real world parameters and gives the analog output. So if I want further processing using microcontroller, so I need to convert analog output provided by sensors and transducers to digital, then do further processing. So ADC is an important module which is required for an embedded system, and we must learn how to write how to configure and write program to convert analog input to digital. Basically there are two types of signal: analog signal and digital signal. Analog signal will measure a parameter and plot with respect to some other parameter. X-axis will have one parameter and y-axis will have another parameter. We'll plot that parameter with respect to another parameter. So this is an analog signal. Whereas digital, there are only two states: on state, off state. So logic 1 and logic 0. So example of analog signal is a speedometer displaying speed with respect to time. Other examples of analog signals are sensing temperature from the temperature sensors. So temperature versus resistance. As and when temperature increases, the resistance value may change. So I'll plot temperature versus resistance. So or light, the ambient light or intensity of light with respect to resistance. So this is what analog signal. Whereas the digital, there are only two states. A switch can be on or off. A door, if a room is open or closed. Only two states. What is ADC? It is an integrated circuit which we use to convert analog signal to digital. So as I said earlier, all real world signal sensed by parameters sensed by sensors or analog in nature. If we do further processing using microcontroller or microprocessor, we need to convert analog signal to digital. So it acts as a bridge or link between analog world of transducers with the digital signal processing. So this is a continuous analog signal. So we'll take the samples from that analog signal and we'll convert that to digital for further processing. There are two types of the two methods and the two processes involved in ADC conversion. The first one is sample and hold, and the second one is quantization and encoding. The sample and hold is nothing but taking discrete samples from this analog input signal at regular interval of time. So taking samples at regular interval of time from this analog signal is called sample and hold. That is done by a sample and hold circuit inside ADC module. So once I have sample and hold signal, then we do further processing called quantizing and encoding. What is quantizing? Quantizing is a breakdown of analog value to a set of finite states. For example, if I have analog input, a voltage of 0 to 10 volts, in that V minimum is 0 volt, V maximum is 10 volt. If we convert this analog input from 0 to 10 into 3-bit digital output, say for example, so we need to break down this 0 to 10 volt range into equal number of sets, finite states. So how do we do that? So that is what quantization. Q equal to V max minus V minimum divided by 2 to the power of number of bits. So whereas V max is 10 volts and V minimum is 0 volt, divided by 2 to the power of 3. 3 is the number of bits, that is 3-bit digital output I want. So Q I'll get 1.25. That means 10 volts, that is 0 minimum voltage, 10 maximum voltage. So that is divided equally by 1.25 volt apart. So if I do so, there will be 8 finite states. So 0 to 10 volts, I'll break down 0 to 10 volts by 1.25 voltage apart. So I'll get 8 states, 0 to 1.25, 1.25 to 2.5, similarly 8.75 to 10 volts. So there will be 1.25 difference between each. So this is also called as resolution of ADC. So we'll discuss that later. So this is what quantization. So breaking down the input voltage by equal number of sets of finite states is called quantization. Encoding is assigning that breakdown voltage a digital value is called encoding. So I broke down the 0 to 10 volts into 8 states. Each is differ by 1.25 volts. Any voltage between 0 to 1.25 will be converted to digital value 000. Any voltage between 1.25 to 2.5 is converted to digital value 001. So assigning these finite states these digital value is called encoding. This is the another process involved in A to D conversion. Let us not go in depth of what is quantization and encoding. Let us understand ADC of MSP430. MSP430F5529 has 12-bit ADC. That means if I apply analog input to ADC module of MSP430, it gives a 12-bit digital output. There are 16 individually configurable channels. So MSP430 has 16 channels. There are 12 external channels, 4 internal channels. So 12 external channel means from real world 12 different analog source I can connect to these 12 external input channels, and internally there are 4 channels, 4 sources, so I can use those channels for converting to digital. So totally 16 channels, 12 external channels, 4 internal channels. MSP430F5529 has internal temperature sensor. We'll see that later. We have option of selecting reference voltage. The reference voltage is an important thing. Based on this reference voltage only the analog input is converted to digital. So we need a reference voltage. With reference to this voltage, any analog input applied will be converted to digital. So we have option of selecting different reference voltage. We can program, in program we can select that. So option of selecting 1.5 volt, 2.0 or 2.45 volts as reference voltage. There are 4 clock sources available for ADC module. The first clock source is ADC oscillator, auxiliary clock, master clock, sub-master clock. So these are the 4 clock sources available for ADC module. So we can configure ADC module to use any one of these clock sources. We have a sample and hold circuit, so we can program it and select the required sampling rate either through timer or through software. So sample rate is nothing but taking the sample at regular interval of time. That rate I can select using programmatically. So that rate I can select through timers or through software. And lastly, there are 16 result registers. So I told there are 16 channels, 16 different analog source I can convert to digital. So for each of the channel I have one register. In this register I find the result of A to D operation. So this is the internal diagram of ADC module MSP430F5529. So you have 12-bit ADC core. This ADC converts any analog input applied to 12-bit digital value. So where do I apply analog input? So I have 16 channels, A0 to A15. There are 12 external channels, A0 to A15, and there are 4 internal channels. So 12 external, 4 internal channels. So to these channels, so I can apply analog input and select one of the channel analog input voltage to be converted by the ADC. There is an internal temperature sensor, has got inbuilt temperature sensor, so we can measure the temperature of the processor by selecting this channel. So there is also a voltage divider. I can convert internal reference voltage. So the 1, 2 and these 2. These are the 4 internal analog input channels. We can select a reference voltage. So this circuitry we can use to select the reference voltage for A to D conversion. We can select through program a reference voltage of 1.5, 2.5 or 2.0. So using this circuitry I can select the reference voltage required for analog to digital conversion. There are 4 clock sources available: ADC oscillator, ACLK, MCLK, SMCLK. I can select any one of these clock source for ADC module. Sampling rate can be selected by this circuitry. Using a program, I can configure this circuitry to select the required sampling rate. So the sample and hold circuit will take the sample from analog input signal. It depends on what I configure here. Using this circuitry I can configure the different sampling rate. Once the ADC module completes the conversion, the result of analog to digital conversion will be in these registers. So there are 16 registers, ADC12MEM0 to ADC12MEM15, 16 registers, each register for each of the channel. A0, analog input channel A0, I have 1 register. Analog input channel A1, I have a different register. Analog input 15, I have different register. So in this register I'll find the result of analog to digital conversion. So let us now understand the registers which is required to configure ADC module. The first register is ADC12MCTL0, ADC12 memory control register 0. So using this register I can select the channel. So you can see there is a pin diagram MSP430F5529. So P6.0 is multiplexed with A0, means channel 0, analog input channel 0. Analog input channel 0 is multiplexed with P6.0. So to select that channel I need this register ADC12 MCTL0. So you can see here, so bit 0 to 3, so if it is 00, so analog input channel 0 is selected. If it is 00, analog input channel 0 is selected, and the V reference I have selected is AVCC, that means 3.3 volt. So I am not configuring a V reference module to generate a reference voltage of 1.5 or 2.0 or 2.5. I am using V reference as 3.3 volts. So if I load ADC12 MCTL0 00, so I am selecting channel 0. I have selected reference voltage of 3.3. So by loading different values to this register, we can select any of the channels, different channels, and convert analog input applied to these channels to digital value. The second register is ADC12CTL0, analog to digital conversion control register 0. Using this register, we can select or configure the sampling rate. So we need to take the sample from the analog signal at regular interval. So this registers will help us in selecting the interval between each sample. So I have selected 64 cycles. So that means every 64 clock cycles I'm taking one sample from analog input signal. So also this register is used to switch on the ADC module. If ADC module, if I want to make it operate, so ADC module should be on. So therefore by using this bit I can switch on the ADC module, and using this register I can configure the sampling rate. So ADC12CTL0, I have loaded this value so that I'm taking sample for every 64 cycle, and this will switch on the ADC module. Third register is ADC12CTL1, ADC control register 1. Using this register I can configure sampling rate generated by sampling timer or by the timers. Let us go to this slide. So sampling rate can be selected by the timer. Sampling rate can be selected by the timer or from the software. So if I select the software control, the clock from ADC oscillator or any of the clock from the different source will come here and goes to the sampling timer. Since I'm going to use these bits to configure, to take the sample for every 64 cycle, this sample timer will generate a clock so that I'll take 64 samples to acquire 64 cycle to acquire one samples. So I'm configuring ADC for software sampling rate. The clock from ADC12 OSC I'm applying to sample timer. Sample timer will generate clock every 64 cycles. I'll take sample from the analog input signal. So to do that, so I have to load ADC12CTL1 this value so that I'll take sampling signal from the sampling timer. I need to switch on enable the ADC and start conversion. So I need to use ADC12CTL0. It has got bits to enable ADC module and start conversion. So you can see here by setting the bit I will enable the ADC module, and by setting ADC12SC I'll start the conversion. So I have to do that using ADC12CTL0. Once the ADC module starts conversion, it will take some time to produce the digital output. I have to wait till the ADC module generates the digital output. So how do we wait? So there is a bit in ADC12CTL1 register, ADC12 busy. So this bit will be set when the ADC conversion is in progress. Once ADC module completes its job, completes the conversion, this bit automatically clears to 0, indicating ADC conversion is over. So in the software, in the program, I need to wait until ADC12 busy bit is cleared to 0 by the hardware. So using while statement, I can wait until ADC12 busy clears to 0. If it is set, ADC conversion operation in progress. If that bit is cleared, then it indicates ADC conversion is over. Once ADC conversion is over, the result will be in the result registers. There are 16 result registers, so I need to choose the specific register because I've used analog input channel A0, so therefore I need to use ADC12 MEM0. If I use A1 channel, then I have to use ADC12 MEM1. So after conversion, I'll find a 12-bit digital value in ADC12 MEM0. So let us now write the program interfacing a potentiometer. So when using this potentiometer, I can get a variable voltage of 0 to 3.3 volt here. That I am applying to channel A0, channel 0 of MSP430, so which is multiplexed with P6.0. So let us see the demonstration of this. So I have used a button here to just to indicate the pot variation. So initially the voltage I'm getting at this pot is 0, so I'm getting digital value 0. So if I vary, now it is 0.8056 millivolts. So for that I'll get digital value 1. If I further increase, I'll get 2. So how do I get this? So for that we should know the resolution of ADC. So what is the resolution of ADC? The resolution of ADC is defined by V reference by 2 to the power of n. What is the V reference? V reference I have taken 3.3 volt divided by 2 raised to n. N is number of bits. This ADC is generating the digital value. So 3.3 volt divided by 2 to the power of 12 gives me 0.8056 millivolts. That means this ADC will respond for every 0.8056 millivolt change. I'll observe change in the output. So I mean to say, if it is 0 volt, it produces a digital value 1. If it is 0.4 millivolts also, it produces digital value 1. If it is 0.8 millivolts, then also it will produce digital value 1. So if it is 0.8056, it produces digital value 1. That means from 0 to 0.8056 millivolts, it produces digital value 1. So 0.8056 plus 0.8056 is nothing but 0.16 millivolts. So if I apply that, I'll get digital value 2. So plus 0.8056 millivolts, I'll get 3. Plus 0.8056 millivolts, I'll get 4. So that means for every 0.8056 millivolt change, I can observe change in the digital output. So the maximum value is 3.3 volt. So for 3.3 volt, I'll get 4096 is nothing but F3Fs. So for 3.3 volts, I'll get digital value FFF. FFF is nothing but 4096. So the aim of the program is to read the analog input, convert that to digital using ADC. Once a specific voltage is reached here, I want to switch on the LED. So for a specific voltage X, let us say I'm getting 512. If this value, digital value is greater than 512, if digital value is greater than 512, then I'm going to switch on LED. So let us see the program. So this is the program. So I have declared a value and a variable called value underscore ADC. Stop the watchdog timer. Configure P6.0 for analog input operation. Already I told P6.0 is multiplexed with channel A0. So I'm converting analog input applied to channel 0, analog input applied to channel 0 to digital. This channel is multiplexed with P6.0. So therefore I have to configure P6.0 for analog operation. So next, P1.0 I have connected an LED. P1.0 I have connected an LED. So this pin must be configured as output. Next, I have to select the channel. The channel is channel 0, channel A0. So therefore I am loading 00 to ADC12 MCTL0. I am selecting a sampling rate and turning on ADC module. Next, I want a sampling rate clock to be generated by sampling timer. So I'm loading ADC12 CTL1, this value. Next, I'm enabling ADC module so that it can start conversion. So I'm entering an infinite loop. By loading this value to ADC12 CTL0, I'm starting the conversion. Once ADC starts conversion, ADC12 busy bit will set, indicating conversion in progress. ADC module will take some time to produce the digital output. So meanwhile, ADC12 busy bit will be set. Once ADC conversion operation is over, ADC12 busy bit clears automatically. So that will fail the condition. So as long as the conversion is in progress, I will be in this loop waiting for ADC to produce the result. Once ADC completes the operation, ADC12 busy bit clears, condition fails, comes out of the while loop. So I have result in ADC12 MEM0 that I am taking to a variable value underscore ADC. Now I am comparing value underscore ADC with 512. If it is less than 512, I am switching off the LED. If the ADC value is greater than 512, I am switching on the LED. So let us see the live demonstration of the code, the conversion. So let me explain the connection. So here I have used 5K port. One end of a port is connected to 3.3 volts on this side. Other end is connected to ground, and the middle terminal is connected to P6.0. Take it closer. So I have connected to P6.0 yellow wire. So here in this yellow wire I am getting a voltage from 0 to 3.3 volt. I can vary the voltage from 0 to 3.3 volt. That I am converting to digital. If the voltage on this wire reaches a certain value, I am going to switch on the LED. Okay, that is the requirement. So let us build the program. Already I have downloaded. So you can see here I am getting value ADC, the variable I am getting some value 30, because this value I am getting for the port adjusted for some value, and you can see the red LED is off. So if I vary the pot, you can see I'm varying now, so it's increasing. That means I'm varying the analog input voltage. So now the value is somewhere around 509. So the LED is off. So if I further increase, so if the digital value cross 512, I want LED to be on. So I'm comparing digital value with 512. If the digital value is 512, I am switching on this LED. So if I vary the knob, so I'm increasing. Now let me reduce it. So I'm reducing, so it goes off. So I'm increasing, it goes on. Okay, so by varying the analog input voltage, so based on the output it produces, I'm doing some action. So this is all about demonstrating internal ADC of MSP430F5529. So hope you understood. I'll meet you or join you with next video. Thank you.